Good morning. I wanted to provide this video along with PowerPoint slides from last night since the sound went kind of bad. So I'm starting out on slide number 4. The number 4 can be seen in the lower right hand corner of the slide. And to load an Excel file into PSPP, we have to convert it to CSV file first. So we save as type, and scroll down and look for CSV, comma, delimited. And the next slide, number 5, when we open PSPP, that's what it looks like. And then we click on File and Import Data. And slide 6. And next slide, after clicking Next and Apply, we see this in slide 7. This is my mock data. And in variable 1 is the number of observations, or patients in this case, and 2 and 3 are pre and post intervention, we'll say for resting heart rate. So we can do a paired t-test for this, for these data, meaning that, for example, patient number 1 has pre and post, patient number 2 has a pair pre and post, and so on. If variable 2 and 3 were different populations or groups, for example, boys in 2 and girls in column 3, then that we would need a 2-sample t-test for that. But as it is, they're not different. Each the 62 and 61, for example, for patient number 1, belong to patient number 1. So that means we can do a paired t-test. The next slide is a histogram of the variable number 2 we see in the bottom left corner of this screenshot. And by the way, you're welcome to do screenshots for your homework. Paste it into a Word document. And this histogram has questionable, normal, questionable, severe. Certainly it's a departure from the bell curve, but is it severe? Does it negate using a t-test? And as I mentioned last night, histograms are not maybe the ideal method of determining normality for small samples such as this. Whereas probability plot is probably more appropriate for small samples, and looks like, according to this, it's acceptable normality when the data points are along this line. That's slide number 9. Slide number 10. We're ready to do the t-test. So we'll click on Analyze, and in the drop down we click on Compare Means, and then we have another drop down options over there, and we'll click on Paired t-test. The next slide, number 11, we get this window, and we'll load the variables into the window test pairs. We'll do that for both variable 2 and 3. Variable number 1, as you might recall, is just the list of patient numbers. So in test pairs window, at least in the program I'm using, the version, it seems that only one of the variables shows up in test pairs window, but you'll want to click on both. Click once, then click the arrow to load it in, and then do the same with the other variable. And that second one, may not show up in test pairs, but it's there. So just a little bit of a quirk, I guess, in PSPP for this. And then at the bottom of your screen on your computer, you'll see a red circle where the arrow's pointing. Click on that for your output. And slide 13 shows the output. And that this is pretty much a standard output for the t-test. So there's 3 rectangles of data. The upper rectangle, upper left there, we see mean and number, standard deviation, and standard error of the mean. And we'll, for now, ignore the correlation there. That's kind of a bonus extra information. Then the third rectangle, the long one on the bottom there, we see data results for differences between, if you recall what we're doing here, we're looking at pre versus post intervention, resting heart rate, we'll say, and we can see the average difference is 1 and standard deviation is not much at all. Same with standard error. And then the 95% confidence interval for the difference is between 1 and 1, so not much difference at all. And the degrees of freedom, 9. T value is high. And the significance there, it's a two-tailed significance. That means we're looking at whether the difference, whether the post resting heart rate decreased on average or maybe it increased. So that's the 2 part. If we're only interested in one way, interested in whether it decreased, then we'd use a 1-tail, but that's unusual. Typically the 2-tailed is used. I use it in my research. I'm interested in whether it goes both ways for my research, whether it's resting heart rate or some other variable of interest. Slide 14, here's some examples. Let's go back to 13. The significant box there, it says 0.000. So the researcher sets the level of significance. Usually it's 0.05. And a p-value less than or equal to 0.05 in that case would be considered statistically significant. So the 0.000 is obviously less than 0.05. So this p-value here is statistically significant. So in order to say whether a result is statistically significant, we need to know the p-value, 1, and 2, we need to know what the predetermined cutoff was, sometimes called the alpha, sometimes called the level of statistical significance. That's the 0.05 that the researchers established, and that's usually what it is, 0.05. If it's some other value, then the researchers need to explain that and defend it. Same with using 1-tail or 2-tail. The researcher needs to explain that. So if a study is significant, it has to do with that p-value, nothing else. It does not have to do with the thousands of patients in the study or whether the study was done at a very famous university or none of that matters when it comes to talking about significance in statistics. It has to do with the p-value and whether the p-value is less than or equal to the pre-established alpha level, typically 0.05, or whether it's greater than. If a paper is not reporting a p-value, then we cannot say whether the results were statistically significant or not. But we can say that we don't know because they did not report a p-value. So slide 14, some examples here. Let's say for all four of these are predetermined level of statistical significance. We'll say we're using the conventional 0.05. So the first one there, 0.04, is that statistically significant? Yes, it's less than 0.05. If it was 0.05, that would be statistically significant also. Technically, statistical significance is less than or equal to the alpha level. 0.2, that's greater than, so that's not statistically significant. Less than 0.05, sometimes researchers just put that, and they don't put the precise value. So that would be statistically significant. P greater than 0.05, that would not be statistically significant. And the P stands for probability, and a common interpretation of the p-value is probability that the difference occurred by chance alone. So going back to slide 13, 0.000, very low probability that the difference happened by chance, and that gives us confidence that the result was due to something else, like the intervention. In Excel, we can set up our data like this in slide 15, and then we click on the FX, which is right above the letter D, a little bit to the left, and above the letter D, click on FX, that is function, and we see the list there, and look for t-test. And array 1 would be the first variable is the pre-heart rate. Array 2 is the post, and just left click on the numbers and drag the mouse down to include all the numbers from 62 to 87 for the pre. And tails, there's the tails again, where typically the researcher is interested in whether in this case the post heart rate went up or down, not just up or not just down. Type 1 in Excel, you can read the type is the kind of t-test. Paired equals 1, and we have paired. Each of those rows, for patient number 1, pre and post belongs to patient number 1. So it's not two different groups. Patient number 1 has both of those, 62 and 61 belong to patient 1. 58 and 50 belong to patient number 2. So there's just one group of patients here, each having 2 columns, but just one group. And we see our p-value there in the middle of that window on the function arguments window, 0.005. Is that statistically significant when we have our conventional level of significance at 0.05? Yes, it is. So the average pre was 69, average post 63.2, we see there, and so that decrease probably did not happen by chance. And a lower resting heart rate is in general considered better than a higher resting heart rate. I say in general, if it goes low into the 40s and there's no explanation, the person is not athletic and so forth, then that might be a problem. Bradycardia may be a medical condition. Slide 18. This is a screenshot of Stata, another software program. So what I use in my research. And it has a, shall we say, a back page for the data. It looks like the screenshot for Excel. And I click on statistics, and similar to PSPP, you get a drop down. And so the thing with Excel is a little trickier to get output. But in PSPP, it's a little more user-friendly, as with Stata, to get output. So for my paired t-test, it gives me this window in slide 21. First variable, second variable, pre and post. And here's the output in slide 22, similar to PSPP. In Stata, it's giving a confidence interval for both variables, as well as what PSPP did. It did that just for the difference. And we're getting a similar p-value here as we did in PSPP. Statistically significant anyway. The 0.0051 is the two tails. The p-values on the left and right, those are one tail. But the one in the middle, the 0.0051, that's two tails. And we see that by the absolute markers around the t, whereas on the left, t less than t greater than t on the right. Those are one tail. So thank you, and again, I apologize for the sound issues, and hopefully I'll have that improved the next time. Have a great day.